Today we will be talking about horizontal control and how to implement this using traversing. In horizontal control, in traversing, we are trying to find the precise coordinates of points on the horizontal plane. So the coordinates, they are the eastings and the northings. As you know, we have different methods of achieving the horizontal control, which means finding the coordinates of the control points or control stations, and today we'll be talking about traversing. In future presentations we'll talk about the other methods. So in traversing, first of all we're going to say that this is a small to mid-size application area, and especially and mainly in construction sites. So in construction sites we always or most of the time we will have traverses that will control the activities, surveying activities in that project. What are the measurements? We will be doing all angles and all course lengths. In case we have a closed traverse or we have a link traverse, both we will be doing the measurements of angles and distances, or angles and the course lengths, and all over for all of them, and all the interior angles. In case of a polygon, when it is a link traverse, we will be measuring the distances, and also we'll be measuring the angles, either counterclockwise or clockwise, depending on what did we do in the field. Either one will be measured. For the horizontal control that is needed, we need, in the case of the traverse that is polygon type, we need the coordinates of the starting point, which is the control point, and we need the azimuth of the starting line. In case of a link, we need the coordinates of a starting control station and the starting line, the azimuth of the starting line, while at the end we need the coordinates of the control station, and we need the azimuth of the last line. So in the closed link traverse, we need control at the beginning and control at the end. At the end, we will use a solution method. For example, the compass rule, which has been used like 99% of the time when we are doing manual calculations, or what we call stepwise calculations. We will use the compass rule, while the best thing, which is a little bit more complicated or more advanced for the regular students of the surveying courses, we'll use the least square adjustment. And because the least square adjustment here, it is a nonlinear model between the observations and the unknowns, we have to come up with initial values in for the unknown coordinates, for the unknown stations. We always remind you that what is the purpose of traversing, or in the case of horizontal control, is that we need to find the exact or accurate, precise coordinates of the unknown station, which are the easting and the northing. Now also a reminder, what is the meaning of traverse solution? That means all the activities to compute the coordinates of the unknown traverse station. We have three components that are needed. First, we need the starting control. We just mentioned that. And we need the field measurements. Field measurements are usually the length and the angles of the traverse. And now we have to determine, also we have to choose the method of computations. Why do we need starting control? This is a question we always explain, and this is why. First of all, when we are talking about the starting point here, or the first control station, the control station, if we do not have a control station, that means we only have the measurements of the angles and the distances. That does not mean we know where there is location of the traverse. Can be here, can be here, can be here, can be here. So it can be anywhere, because we do not have any clue where this traverse is. So once we have the coordinates of a station, that's it. We know where the traverse is starting from. All right. So let's go again to the azimuth of the first line. We know this is our starting station. But around the station, this traverse can be oriented in any direction, as you can see. Like this, the traverse is in its place with respect to this control station, but it can be rotated in any direction. That's why we need the azimuth of the first line, so we can fix the rotation, the orientation of that traverse. That's why we need a point, a control station, to determine where is the location, and we need the azimuth of a line to determine the orientation of this traverse. In the field measurements, in the case of traversing, we need all the interior angles in case of a polygon traverse, and we need the lengths of all the sides, or we call it the courses. So we need all the angles and all the courses. So length of all traverses and all the angles at the traverse station. Now, in the solution, we have different methods, but two methods that have been used all the time. At the beginning, we have the stepwise traverse calculation. What do we mean by stepwise? It means like we do something and then continue on something else. So here in the stepwise calculations, which is the regular, this is the compass rule. We used to use this compass rule. First, we adjust the angular disclosure, calculated and adjusted. Then, from the adjusted angles, we calculate the azimuths of the unknown courses, and then, of course, relying on the azimuth of the first line, and then calculating the departures and latitudes from the measured lengths and the adjusted azimuths, or calculated azimuths from the adjusted angles, and then from these departures and latitudes, we'll be able, based on the closed traverse or the ring traverse, we'll be able to calculate the linear misclosure. Once we calculate the linear misclosure, we fix it, and finally we will be able to calculate the rectangular coordinates, easting and northing, of the traverse station. In this kind of solution, this is a linear solution. It does not need initial approximations, but due to the stepwise solution or nature of the solution, any errors that remains here will be inherited by the next step. Any errors here will be inherited to the, so this is the main disadvantage of this kind of a solution. Its advantage, the most important advantage of this, is that it's a linear solution. We do not need initial approximations of the points, and usually it gives a decent, good results, but it is not the best results. So we can do this solution manually. In the surveying course, we used to do this, the compass rule manual implementation. But here we will learn how to do that using a software. And this software is called the Adjust software. Actually, we'll use the Adjust software, which is an academic package for all the calculations that we want to do, either manual or the least square solution. In the least square solution, here, this is the other method, least square solution. Also, we can do it manually, but this is non-linear. It needs iteration. If you are not trained to do that, you don't have enough background, then this solution will be very, very complicated, let's say. It will be time consuming. You will introduce so much errors, but luckily we have a software like the Adjust software, and it will enable us to solve this this type of solution, traverses using least squares, just using this software. And all what we have to do is prepare the input. So this software, which is the Adjust, it will take the input as data files, and then we will just organize the input as to the format that this Adjust software takes it, and then we will just plug in the data files and we get the results. So let's start with the stepwise traverse solution using the software. We do not want to go to the manual method, we just want to go to the software. So as we said, this software, which is called the Adjust software, it uses text files, plain text files that can be opened, created, or modified using Notepad. And we have, for this software, we have to have the extension of the file, the type of the file, as a dat. So any file must have a dat, and after the processing of the file using the software, the result will go into the same file name but with an extension of a out. And as we said, this is the stepwise solution, but it will be implemented using the adjust software. The best thing to explain the procedure is through an example. By the way, this you will see in the examples, you will see a lot of codes, let's say, next to the example, and this code is just a reference for me. And this reference, it enables me to search for the Excel files, AutoCAD files, Visio files that I prepare for these examples. So just to skip this code, it is just something for my reference. So what we have here, we have a polygon traverse that is A, B, C, D, F, and A. And these 5 stations, one of them is a control station, which is point A. And this point A here, we will use it as the control station. What are the coordinates? EA and NA, they are 20 and 20 meters. What do we need more? We need the azimuth of the first line. So this first line is line AB, and we have azimuth of line AB equals 24, 53, 3.5 seconds. So 24 degrees, 53 minutes, and 3.4 seconds. What about the measurements or the observations we made? As we said, we have to measure all the interior angles, A, B, C, at the traverse stations, A, B, C, D, and F. And we have the measurements of the lines, LAB, LBC, LCD, LDF, and LFA. For these are the distances, and these are the angles. As you can see here, we have a direction indicator. We will be going through the stations in a clockwise direction. A going to B, going to C, going to D, going to F, and back to A. Of course, we can start from A, go to F, go to D, and then continue the cycle, and then B, C, and go back to A. What is the difference? In the procedure, in the solution, there is no difference. The same results will be reached, but in preparing the data file, there is a difference. I will show you the difference between these two methods as we go. When using the adjust software, we have to prepare the input as a text data file and according to the format that adjust understand. So we have to start with one line and the other line and the other line as follows. Every method, every solution, it has its own format. Mainly this will be different. The calculation is stepwise solution, but the other ones in the triangulation, trilateration, and the least squares in general, it's almost the same procedure, but we have different input every time. But once we know one format, we will follow like the others. So this one is the most different let's say format for preparing the data file. So the data the blue lines, they are not part of the file. So this is just for the clarification. So the line, this one does not belong to the, we don't have to put it. We put only everything after that. So line 1 in the data file for the traverse calculations, the stepwise solution, it is the title line. So we put a title line, we put whatever, we put the brief description of the problem. Here I put also the ID of the traverse I am solving, just for reference. Then in the line 2, we have to put a list of numbers, and these numbers, they are the number of courses that we have in the traverse, 3, 4, 5, whatever, and direction indicator. Direction indicator, as I showed you before, is it the clockwise or the counterclockwise rotation along the stations. So here, if it is 1, this is a counterclockwise point rotation or point sequence, while -1 is for the clockwise. In our example that we are doing, we are going clockwise rotation from A, then B, C, etc. And that's why we have to put a -1 for that. In line 3, we have to put the azimuth or bearing of the first course. Of course, we have to have one azimuth, and that's why we have to put it here. How do we put the azimuth? What is the format? It is degrees, minutes, seconds, and we have to start with the degrees, and then like 23 instead of the degrees, as you used to have like 32 degrees, 52 minutes, and 13.3 seconds. This is entered as just numbers with spaces without the symbols, 32, 52, and 13.3. Then what do we have? We have line 4. In the fourth line of the file, we have to put the length of, we'll take it in a sequential format, is that we want to put the length of the line and the angle that it makes with the, at that station, at the beginning station, and then the other line and the other station. So we have to repeat for all the number of courses that we have here. To repeat line 4, which has two values, one which is the course length, and the second value, it is the interior angle at the control station. This is what we have to start with at the control station, and then we repeat it for the other courses and the other interior angles, not at the control station, at the other stations. At the end, line 5, we said we need a control point. So what are the coordinates of the control station? It is EN control station coordinates. We will put it in meters and feet, whatever the unit system of the example or of the job you are doing. So let's prepare the data file for example number 1. As again, we said the blue text is not part of the input data, it is just clarifications for the thing. Now for the line 1, it is just a brief problem description or title. So for this we can say data file for clockwise 5-sided traverse example, and we put the code. You are free to choose whatever you want for this title. Then for line 2, we have to start with the number of courses that we have: 1, 2, 3, 4, and 4 and 5 courses. And then what is the direction? Direction is clockwise. That's why we will put a -1. So this is the direction 5 and -1. This is the second line. In the third line, we have to put the azimuth of the first course as degrees, minutes, seconds. As said before, 24, 53, 3.4. It is just listed like that with a space between them without the symbols. So we just put the azimuth. Whatever the azimuth is given, we just plug it in this line. Then the next line. The next line, which is line 4, it is about the angles. Starting from the control point, this is the control point. So we started from the control point. We want the angle at the control point, which is angle A, and the length of the line of the course in that direction, in the clockwise direction. So we're starting from A. So this is the first line we have, which is line AB. So we need the angle A, and which is at the control station, and line length LAB. So this is the first line in the format of line 4. So here we put, of course, as we said before, line 4 is repeated for all the angles and all the length, the sides or the courses. So the format is course length, then the interior angle. Look at this. We have to start from the control station. We put the length LAB and the angle A. Then on the second line, we will give the angle B and the line LBC. And this is the second line. And the third line, LCD, we'll go back to LCD, which is angle C and the line LCD. So LCD and line 3 and angle C. Then again, this is the fourth line of line 4. So it is LDF. And then we have the angle D At the end, we have the fifth side and angle, which is LFA, the length of side FA, and the angle F. Here we finished repeating line 4 for all the angles and distances we have. Finally, we have to give the control station coordinates, easting and northing in meters in our case, and based on the number of decimal places here, the solution will be. So if you have like 150, we always have in the meters, we have 3 decimal places. For example, 068, these are 3 decimal places. If it is just only 150, you will say 000 just to tell the software that we have 3 decimal places of required accuracy. So we list the 2 values, and here the data file is complete. Let's look at the file as a whole. This is the file as a whole. Again, these are just the number of the lines. Like here, line 1, it is the title. Line 2, number of courses, and the direction of turning, it is clockwise, so it's -1. Then we list the value of the azimuth. These are in symbols. And line 4, you see, we have 5 times the angle at the control point. And then at the end, line 5, which is the coordinates of the the coordinates of the control station, which is EA and MA. These are the numbers in our case. This is the measurements. Here we have the length, and here is the angle, degrees, minutes, seconds, and the length it is, and these are actually, these are the original azimuths. We do not use these. We just use the first azimuth, as you can see here. The first azimuth, the azimuth of the first line, 2453, 3.4, which is this one. These are just extra information. I have it from the original example file in AutoCAD. So these are things that we are not, will be calculated actually. I'm having them here to compare them with the calculated values, but we do not need these values. Well, what we need is the, first of all, the angle and the line. So the angle is 92, and the length of the line is 31. And the line after that, we have the length of the line. It looks like the length of the line is missing here for this line. That's okay, but we need the length of this line and the angle B. So this is angle B, and the length of the line is 17 something. This is the angle, it's 67. This is the second set of angle and side. So we have the side 17 something, it's not just missing here, and the angle is 6714, 45.6. Then we have 21, 41. I will tell you now why we have differences here, and these are this is the angle 217, 26, 58.6. So we have a little bit of a difference, and this difference is due to the following. These numbers that we have here, these are the exact numbers from the AutoCAD file. So these are the exact lengths and the exact angles. But when we do the measurements in the field, we never get the actual and the exact measurement. So I took these values and I added some noise to them. Noise means I added some random errors. So instead of here, the measurement is 31.826. So here I put it as 31.824. And this difference, I added that because I don't want to give the exact length, and I want to see what will happen later on. The angle here, it is 92. I added some noise at the second part, and I said this is the measurement of this angle. So all these lines and all these angles, interior angles, they are measured. Look what happened here in the azimuth. In the azimuth value here, it is 24, 53, and 3.4. I kept it the same because this is control information. I have to put it as it is. But the other angles and measurements, of course, they should have errors. These are numbers from the AutoCAD, which are the exact numbers. We in the measurements, we do not have exact numbers. That's why I put some noise on all of these numbers. So here, 31824, I added, instead of 826, I added 2 millimeters of error. And on the angle, I added some error at the second part. In the second one, the number unfortunately is not there, but it was 17.96 something else, but I put it as 64. The angle, it is 67, 14, 45.6, 67, 14, but for 45, instead of 45.6, I put it as 49.2. And then the line, the next line, it is 21,409. I changed that a little bit by adding the noise. There is one way to do the noise in Excel, by adding Gaussian noise. This is like a little bit of a step that needs some experience, but anyways, I just made this random changes in the numbers to reflect some random errors existing in the data when we collect it. So when you compare these, the last one, which is 105.12, 37.6, I put it 43.2, and the distance here, 27.192, I put it 27.264. These are just to imply the random numbers. So as if these are, because these are the measurements, these are the observations in the field. So I said these are the observations. These are the perfect case. I cannot use the perfect case because in this case I will have no errors. But at the last line, which is the control information about the easting and northing of the control station, so I just given the same thing. So 2020, these are the given coordinates of the control station, and we need the azimuth as part of the initial control, which is 2453.3.4. We'll give it the same value. All other observations, they have some different value from the perfect case from AutoCAD to just reflect the random errors that will happen. How am I gonna implement this in the Adjust software? The Adjust software, it is given to you. There is a link in the Blackboard. You can go and download the software. Once you download it, just double click, it will open. Once you open it, you will see this screen. Of course, this is partial screen, just the top. How do you start the traverse solution using a stepwise method, which is the traverse computations compass rule? You click on this T. This is traverse, and then this software works with different types of traverses. Link traverse with bearings instead of the azimuths, instead of the interior angles. Link traverse with azimuths, so either bearings or azimuths. Link traverse with angles instead of the azimuths or bearings. It will be calculated later. So they gave you like this software will give you the different options. What do we have here? Now we have the polygon traverse with angles. We do not have traverse, the azimuth is calculated for all the lines. We just have the angles. So what are we gonna do? We are gonna select this option. Just click on this radio button and OK. After that, you will be given the dialog box to enter the file name. The file name, you will select the data file that you store the information inside it, and then once you click OK, the solution, the first solution will be given to you, and the results will show in a yellow background. See here, this is a yellow background, and this is just inspection for you to look at the results. Then at the end here, at the end of this window down there, there will be two buttons. One of them is close. Once you close it, the same solution will be stored in a data file with a.out extension. You open it using Notepad and you see the results. So as you can see here, we just put the input values. We did not add any kind of initial approximations of the method, because this is a linear method, step by step. So what are the outputs? If you want to dissect it, we want to like analyze it. Station and adjusted angle, these are the angles that we measured. We measured in the field, and after the adjustment, after the this is what we say. The first step is that we want to calculate the angular disclosure have been calculated, and it was calculated to be 18 seconds. And after this 18 seconds, they are distributed over the angles. They are distributed equally. So each one will be given the correction, and the correction added to an adjusted angle to produce the adjusted angle. So the adjusted angle, it is a summation of the unadjusted angle plus the correction. This is the disclosure, and the correction should be negative because it's a positive 18. So the correction is negative 18 divided by the number of angles here. So it will be around 4 something, a little bit less than 4. So 44 minus almost 4, so it will be 40.8. At the end, these are the adjusted angles. Now, what are we going to do? What are we going to do with the angles? We will calculate the azimuths. So these are the azimuth. This is the given azimuth of the line. First line, which is line 1, 2. The control station is called 1 inside the solution. And then these are the azimuths of the other lines calculated based on the adjusted angles, one by one. The length that we gave to the measurements from the field, they are here, and from the measurements in the field, the lengths and the azimuths, we calculate the departures and the latitudes. What does it say at the top here? It says unbalanced. What does it mean? That means these departures and latitudes, they have linear disclosures because they are measured from good azimuths, calculated from balanced or adjusted angles, but the length, it has some errors. So once we have these, we check the disclosure here in the east, in the departures and in the latitudes. One is negative, one is positive, so we have to fix this before we continue. The procedure in the software will do that, and then we will fix the departures and the latitudes for the here in the previous one. These are the unbalanced departures and latitudes. They are fixed, and these are the fixed ones. The fixed ones, we will use them with the coordinates of the starting station, the coordinates of all other points. So it looks like this one is repeated, this part, it is the same as this one, but we have additional information here. The linear disclosure, it was this, and the relative accuracy of the line, of the software, of the line, or the traverse is 1 to 1600. The area, it looks like it was put as square feet, so the area is 911 square feet. This will be calculated. We'll teach you in a different chapter how to calculate the area from the coordinates of the corner points. For now, this is all what we have to do in the case of the sequential, but the sequence, it was clockwise. What if the sequence was counterclockwise? So we still want to start from control point A, but in the clockwise, we jump to point B. In the counterclockwise, no, we have to jump into point F because this is a counterclockwise. So what is the first line? So the control point is still A, but what is the line that we have to know its azimuth after point A? It is line LFA. So the given azimuth or the line with known azimuth, it should be line LFA, not LAB. So this is the known azimuth, and this is the difference. And then we continue A and LFA, LDF and F, LCD and D. This is the sequence, LBC and C, and finally we have LBC and B, and then finally we have LAB and B. So as we can see here, at the end we have to put this EA and NA, the number. What is the difference? Because we have a clockwise point sequence. Now we have this one, instead of -1, now it is 1 because we have a counterclockwise, and the angles are here. The azimuth now we want to put, it is azimuth line AF because it is the first line that we have after the control station. And if you put the numbers, just rearrange the previous file, rearrange for the values and of the angles and the lengths, you will get the same, exactly the same answers for the coordinates of F, D, and B. So if we look back again, what are the final results of this procedure, of this solution? These are the final results. These are the coordinates of the point. That's what we want. This is the horizontal control is all about. We want to calculate the coordinates of unknown stations. And first one, 2020, it was the given control, but these are the ones that we calculate. We'll give these coordinates to other surveyors, whoever surveyors they want to use these stations now, will use it for their works. When you are in a company, in a construction site, this traverse will be used to set out the works, where are the trenches, where are the footings, where are everything. They will be built based on these coordinates. So now this is the stepwise solution. Now let's go for the least square traverse solution using the same software. Now what will be different? The difference will be in preparing the data file. And we have, this is a least square solution which is nonlinear, and we have to use the software, plus we have to come up with the first initial estimates of the unknown stations, easting and northing. How can we do that? One simple thing is that, as you could see in the sequential here, we did not need initial estimations, so we can run a counterclockwise or a clockwise solution of the traverse, and then we will use these values. We will use these values as initial estimates. So maybe one will ask, why shall we do the solution like this and then do it least squares? What is the reason we said? The reason is that the least squares, it is not sequential. All the angular disclosures, linear disclosures, calculation of the coordinates, they are done in one single run of the mathematical procedure, and the solution will be the best. At the end of this example using least squares, we'll show you the differences between the coordinates of these stations when are solved the stepwise or the least squares. They will be very close, but the differences in millimeters or so, they are the results are better for the least squares. So let's go back to the traverse, and we said the least squares, we can do it manually. We will not do it manually. This is non-linear. It needs a lot of work, but we will do it using the software. For the software, we have to prepare the data file as described for the previous section, but it is a different format, and then we have to come up with the initial estimates. So let's start. In the least square adjustment, we explain the basics and the way to do that in a separate presentation, but here there is a reminder. The reminder is that always when we have a least square solution and we have observations and we have the unknowns, and there is the mathematical model that relates the observations and the unknowns, and this was very simple linear case when we were doing line fit or the vertical network. Like the leveling networks, it was we were doing that using MATLAB solutions. We prepare the matrices and they would do the solution, which are the unknown elevations of the points. Now, that was in the vertical control. But for the least squares of the horizontal control, the observations, which can be distances, angles, and azimuths, are related to the unknowns. We'll show you now the equations, but these are a non-linear relationship. And since we have non-linear relationship, they must be linearized. And once they are linearized, we will put it in a different way of doing the least squares. And based on that, we have to come up with initial approximates of the unknown station coordinates. These are the unknowns. And we have to have an iterative solution to fix the initial approximation. So we start initial approximations, and we will start iterations until we reach a good solution, let's say. And then how are we going to do that? We can do it manually using MATLAB, or because that was for this course, this is beyond the scope of this course, we will use the Adjust software to implement the solution. So these are just an idea. You are responsible of understanding the idea and the way we are doing the least square, the principle, but you will not be doing that using MATLAB or preparing the matrices, because this is beyond this course. So let's see now what is the distance observation equation and how is it related to the unknowns. What are our unknowns? You have a distance that starts from one point to another. These 2 points, maybe they will be both unknowns. One of them maybe it's a control point, or the other is a control point. So we have these possibilities. So what do we have? We have, how do we calculate the length, or what is the observation? How is it related to the coordinates xi? Here we have xi and yi, and here we have xj and yj. So how these coordinates, they are related to the length, to the observation. So we say the observation plus a residual equals, as you know, different delta j minus delta xj minus xi, and this one will be delta, let's say x, and this is square, delta x all square. In our notation we call it delta e sting, and this is square, plus delta y, which is yj minus yi, or in our notation it is delta n, so it is delta n, and this is square. So delta n square plus delta e square square root, this will give you the observation, but with some residual, which is due to the errors. So this is the relationship between the unknowns and the observations. These are the unknowns, and this is the observation, the L, in case of a distance measurement. Of course, squares and square roots, these will make the relationship nonlinear. What about the azimuth? The azimuth, it is between the 2 points, the same thing. If we have one point and the other, we in the surveying course, we learned how do we calculate the azimuth from the coordinates of the points. So we have again delta E, this is how you know it, and delta N, which is, this is the N direction, this is the E direction. Here we are showing it as X direction and Y direction, but tan inverse delta E over delta N. And I don't know if you still remember this famous table. So once we have delta E and delta N, we take the tan inverse, then we will check the signs of delta E and delta N. Positive, positive, that means we have a quadrant 1, and we do not have any quadrant adjustment. We add 0, we do not add anything. But if it was positive and negative, that means we are in quadrant 2. And then we have, so here the C, the constant, the addition, the quadrant adjustment is 0. Here the quadrant adjustment 180, and here is 180. And in the last quadrant, the fourth quadrant, it is 360. If you need more information or more knowledge about this, you can go back to the surveying course. Actually, the surveying course is a prerequisite for this course, and that's why you should know that. So at the end, we have this one. C is the quadrant adjustment. When we take tan minus 1 plus the adjustment here, it should be equal to the azimuth of the line that we measure plus certain random error, certain residual. Now let's see the angle observation. The angle observation, it is the difference between two azimuths. So we have azimuth of the first line IF and azimuth of the second line IB. So the difference between them, this one is the azimuth of line BIF. So here it is BIF. This is the angle, which is the difference between this azimuth and that azimuth. The first azimuth, it is the F azimuth, IF azimuth, and minus the IB azimuth. This is the alpha IF, and this is alpha IB, and the difference between them. So once we take the tan inverse, here we have, for this one, we have the constant might be 0, 180, 180, or 360. And also for the second one, for the IF, we have another constant. So these two constants, we combine them together and we call them D. So this is the observation equation that relates the unknowns XF, XI, and B, and the XB and YB. These are the unknowns. How are they related to the angle observation? All of these, as you see, the tan, and also for the azimuth, we have the tan. So this makes the relationship between the unknowns and the observations to be a non-linear relationship. So these are the three observation equations for a distance, for an azimuth, and for an angle. All of them, they are non-linear. So we need, at this level, we need a software. This software is the Adjust software, academic package. We use it. And we prepare the data, and I will show you now how to prepare the data. We prepare the data and we put it in a file with extension ADAT, and then the ADAT will take it into Adjust the same way we did for the traverse and in the stepwise solution, and then we'll get the results in the same file name but with extension of A.out. So how do we prepare the data? So how we prepare the data, it is something similar to this to the example, but it is different, but in a similar fashion, let's say. So at the beginning, we will have a title. Then we have to put the distances, number of distances, number of angles, number of azimuths, very similar to previous ones. And then the control station. So we measure distances and we measure angles and we have azimuth. At least we should have one azimuth. If we have two azimuths, that means we have one more azimuth measured. So we want to use it. Control stations. How many control stations? Do we have one or more? Actually, in this example, we have just one, which is point A with the 20 and the 20 meters coordinates, and then the total number of stations. So here is the control station. In our case, it was one control station, point A, and the stations here, they are total are 5 stations, which is including the control. So we have one control plus 4 unknown stations. The total is 5. Then the next question, the next lines, normally they will start taking the details of these heading, let's say, control line. So the control line, what are the number of distances? So here, what do we have? At the first line, after the control line, the line that has the basic information, we have the control stations. We need to list the number of control stations, each one with the its X and Y. So the station ID, here we say A, and then space, and the maximum number of characters for the ID of the station is 10 characters without spaces, without any commas. Then we will have X and Y, which are the coordinates of this control station. If you have one control station, like in our example, you will have one line 3. And then we will take the, if we have more, we'll list it, just repeat line 3 for the number of control stations. For the example, as we said, it is only one control station, so one line. Now we come to the unknown station. The unknown station, we said, it is the same thing for the control, we want to put the ID, but the value X and Y, these are unknowns. So what are we going to put instead of X and Y? It is the initial estimations. Where are we going to do that? From where are we going to do this or bring these values? You can run, as we said, stepwise solution like before, and find X and Y from there and plug it here for everyone. So here B, C, D, F, unknown stations, we have to come up with their initial estimates, and we will repeat. Station ID, IDXY, and then repeat IDXY for all the unknown stations, with these being the initial estimated or approximations of the X and Y. Now we have to follow this sequence. You cannot put like the distance observations before. We have to keep the sequence: control stations, unknown station, then distance observations. The distance observations we have to specify from where to where. So occupied station, if you are, for example, point A and point B. So when you want to measure line AB, you sit at A and you measure to B. So this is the occupied station A, and the sighted station, you are looking at B, and this should be B. What is the distance you measure? You put the distance you measure, and this one is the standard deviation of the distance that we measure. We measured it using a certain method, tapes, total station, everything. So we always have a standard deviation of the. If you see something between two brackets, that means this is optional. If you do not put it, then the system, the software, will provide a value for that. This is a standard value, so you better put the standard deviation that you have, and you repeat. For the second distance, the third distance, you have to put the starting point, the ending point, and the value. Starting point and the ending point and the value and the standard. Like if you measure the distance to plus minus 5 centimeters, so it will be in meters, of course, 0.05. This will be the standard deviation, 0.05. And then you repeat. Then, once you finish repeating the line for all the distances, if you have 5, 6, 20, 30, you put it all of this here, and then you jump into the angles, because these are distance and angle observations. So you put in the angle, in the case of the angle, we have the backside station, we have the occupied, to measure the angle, you need an occupied station, we need a backside station, and the foresight station. So we have to have 3 stations, plus you have to put the value in degrees, minutes, seconds, just separate them by spaces, and if you want to add standard deviation, it should be in seconds. 5 seconds, 20 seconds, 10 seconds, regardless, but it will be in seconds. Then you go to the second angle, to the third angle, to the fourth angle. I will show you how you should, where is the back station and where is the forward station. I will show it to you now. But now, after we finish the angles, entering all the angles, in our case, we have 5 angles, so we have to have 5 lines. And here for the distances, we have 5 distances, so we have to have 5 lines. And in the azimuth, it is the azimuth of a line. So we have starting points. So if you have line AB, that means the azimuth of line AB. So we have from point A, this is the starting or occupied station. B is the sighted station. So occupied station will be A, and then B, sighted station. And then what is the azimuth of line AB? You put it in degrees, minutes, and seconds. And then if you have the standard deviation, because we usually put it for a very nice value here, so you can say it is 1 second, because this is a control value. And that's it. You will be done with the data file. So here what we have, same example, but now we have what do we have? 5-sided counter clockwise, and then A is the control station, and B is the point, the second point, everything, and the azimuth is 24, which is the same value, starting station 2020, and these are the same input that we used in the stepwise solution. For the least squares solution, we have to come up with the initial coordinates of B, C, D, and F stations. Where are we going to get it from? Either you manually do that based on your experience, or you have to go and do a stepwise solution like before, and then bring the values into here. So the line 1, I want just to put a data file for 5 traverse stations. Just put these, and then just a title, whatever. Maybe we'll add the least square here, LSQ solution. It would be better to differentiate the solution. I think in the data file, the original one or the actual one, I put the least squares. Then here we have to put what are the number of distances. We have 5 distances, 1, 2, which are 5 courses. The angles also we have 5, A, B, C. These are the here I am also listing them here, A, B, C, D, E. Number of azimuths, we have just one azimuth, A, from A to B. Control stations, we have just one control station, which is A, and the line 2, which is the is 5, 5, 1, 1, and 5. So 5, 5, 1, 1, and 5. As we said, the text in blue, this is a reminder in which line is this. We do not put it in the data file. In the second line, we have to start with the control stations, and the control stations here, we have one control station at A. So here we'll say A is the control station, and the coordinates, they are 20, 0, 0, 0, 0, 0, 0. So the solution will be to 3 decimal places. Line 4 now is for the unknown stations. As we said, either you will get the values. Now we will list point B, and these are initial approximate values. I took it from the solution of the first example using the stepwise solution. And C also, I took all the values. Of course, I removed all the decimal places, because I don't need that. The initial values can be like 1, 2, 3 meters off. That does not have a problem for this case. So we will list all these values. Of course, the 4 and the 4 and the 4 and the 4, they are not part of the line. They are just for reminder which line is this. Now I have to list all the distances one by one. So we have the first distance is A, and this is the second. First distance is AB from point A to point B, and this is the value of the distance, which is LAB. This is from where? From the from here, from this table of observations. We take the values of the length and everything, and the angles also from here. So we come here, the angles, and what is this? 0.01. This 0.01, which is 1 over 100 of a meter, okay, plus minus 1 over 100 of a meter, which is plus minus 1 centimeter. So we are assuming the accuracy is 0.01 plus minus 0.01 meters, which is equivalent to 1 centimeter, but we have to enter it in meters. And the same thing for the line BC. The length is 17 plus minus 1 centimeter, and CD, all of these from the observations table. Now we can go to the next one, which is the angles. What do we have? Angles. Look at this. Angles, the interior angles. How do we enter the angle? We said we need 3 stations to define the interior angle. We have the back station, and we have the occupied station, and we have the 4 station, the 4 side, the back side, and the occupied station, the vertex of the angle. So in our case, we have to have it as a clockwise angles, and we will start B, and then A. B is the back side, A is the 4 side, and then F is the force, B is the backside, A is the occupied station, and F is the foresight station. And then we turn. Where are we going? The next angle. Next angle is angle B. Of course, we put the angle, degrees, minutes, seconds, and here 10. What does it mean? Accuracy is plus minus 10 seconds. So now CBA, when we want for angle B, it is C as we just turn the whole thing. C is the back station, B is the occupied station, and A is the foresight station. Then we go to C. C, it is D as the back station or backside station, C is the occupied station, and B is the foresight station. If you follow, you will see that I repeated all this logic, let's say, the method of defining the angle for all of these, and all the angles, they are plus minus 10 seconds. Now it is the azimuth, and the azimuth is occupied station. It was A, station A, and sighted station, it is B. So this is from A to B. And what is the value? 24, 53, 3.4, and this is plus minus 1 second. And this is the last line in the data file. The data file, after that we are ready, and here are the listing, 5 distances, 5 angles, 1 azimuth, 1 control station, and 5 is the total number of stations. Start with the control station, then after that we have 4 stations, B, C, D, F, and these are the control coordinates, but these are the approximates for the other stations. And then the distance, we have 5 distances, the values and the accuracies, which is 5 centimeter plus minus 5 centimeter, or 1 centimeter, I think. Then here we have the angles, and after that we have the value of the angle, and we have the accuracy, which was 10 seconds. And at the end we have the azimuth, and the azimuth is plus minus 1 second. Here are the values. Here are the values that we have. I try to change the color, so you will see each group is a different group. So here the first one is the control line. Of course, this is the title line, and this is the control line, which has the number of stations, number of distances, everything. This is A is the control station. These are the unknown stations. These are the distances. These are the angles, and this is the azimuth. So you cannot go wrong if you just take care of doing things, understand the sequence, and put them in a table. And after that, we are ready to go to the adjust software. We start the software, and then this time we do not go to the traverse option here. We go to the network option. This is the horizontal least square adjustment. So all what we have to do, once you see this, you can just click OK, and the default values will be taken. So you don't have to enter anything. You just click OK. Once you see this dialog box, don't worry about anything. Just click OK and continue. It will ask you for the file name. You give it the file name. So here you select the data file, and once you select it, the solution, initial solution will be, or let's say a solution will be showed on the screen with a yellow background for you to inspect it. You just look at that. After you see that everything is okay, click close, and the results will be written to the output files with the a.out extension. So this is the output. This is the output of the least square. So what do we have here? See what the program will give you. This is the same title. As I said, I put that this is an LSQ example to differentiate it from the stepwise. Number of control stations is 1. 4 are the number of unknown stations. 5 number of distances. 5 number of angle measurements, and 1 azimuth. And here are the approximate initial approximations for the unknown station. This is what we entered. And then control station. This is the exact value of the control station, 20 and 20. And then distance observations, This is what we observed from the field, and we enter that distances plus minus 1 centimeter, 1 centimeter, everything. This is all what we have entered into the data file. The angles also what we entered in the data file. The back-sighted station, occupied, and the forward station values, and plus minus in standard deviation in seconds. At the end we have the azimuth observations. We have 1 observations plus minus 1 seconds. After that we are given the adjusted station. What are the adjusted stations? It is the coordinates of the unknown stations. So first we started with initial approximations, but now we have the final solution, which is the x and y, or easting and northing, of the unknown. And this is the result. This is the result. If I show you and tell you what are the results, where are the results, you have to circle or tell me that these are the results. This is what we are after. Of course, here it will give you standard deviations in the x and y directions, and we'll not go into what are these. These are different statistics about the maximum and the minimum along the error ellipses, we call it. We did not take that. And the root mean square error of the radial error. Don't worry about all this. All what we want is this x and y values. Adjusted distance observations. These are the observations when we said Lij plus what? Plus the residual. So once we have the residual here, and then we can calculate this one, which is, let's call it L hat Ij, to equals the observation plus the calculated residual. So this is because the observations, we have distance observations, we saw that, the adjusted, and here the angles. It is like when you say the adjusted distances, it is like after removing the linear disclosure. And here it's after the adjusted angles, after these are the residuals. This is after the removing the angular disclosure. And here after, if we have for the azimuth, if we have adjustment for the azimuth observation, so that it was very small, so it's about 0. So now now we have the observations and the adjusted observations. As we saw, the adjusted distances, adjusted angle observations, and adjusted azimuth, these are the values of the observations after removing the misclosure in each of them. But what is the difference is that the linear misclosure, the angular misclosure, the misclosure in the azimuth, they are found, calculated, removed, adjusted in one step, in one solution. It is just not like stepwise procedural one like what we saw in the first solution, which is the compass rule. It's not like the compass rule. Here it is done in one shot. So let's see now what are the stations in the case of the least squares, and in the case like for point B or station B, 33.37. This is what we got from the least squares for x and y for the easting and northing, and here easting and northing for the stepwise, which is the compass rule. So what is the difference here? Let's see that here we have a better representation. Here we have difference in x and difference in y. So here it's about 2 centimeters, 1.9 centimeters, and here 7 millimeters, 2 millimeters and 20 millimeters, 6 millimeters and 9 millimeters, 15 millimeters and 5 millimeters. These are the differences. Yes, you can look at these and you are saying we have 33, 45 meters, 66 meters, whatever the coordinates, and the calculated coordinates, the differences are just maximum was 2 centimeters almost, or 19 millimeters. Yes, there is a difference, but which one would you take if you are doing really precise horizontal distance, horizontal control? You have to go for the least squares, and take these values for the coordinates of the points. These values, what you are going to give to the people who are working, surveyors, whatever, they want to benefit from those stations. Of course, these stations will be monumented on the ground. That means a clear pointer, clear marks on the ground, like the benchmarks before. We will be also doing this in the case of horizontal control. This is another example. You go through this example, and then it is the same exact thing. We have a procedure, we have a closed traverse, and we have control station. We have one control station here, and we have the measurements for the angles. We have control station distances, and we have the angles given, and then we have the length, and sigma is 5 centimeters here. This is the length of each side, and here are the angles, and sigma is 15 seconds. We have of course, we have the azimuth. We have to have the azimuth, starting azimuth, and the coordinates of the point. Here we have 10,000 and 10,000. We prepare the data file. We prepare everything. This is the what we have, and then because we wanted the sequential stepwise solution to have the initial values. So we solved this example first using, it is a clockwise point, using the linear system. This one is a stepwise, like what we did. Previous example, we solved it twice. One using stepwise is a compass rule and least square. Again, this one is the compass rule. So this is the data file for the compass rule, and then we have this is the file itself. If you want to put it in a file and run it and check the results, and then these are the where's that? No, this is the data file for the compass rule. This is the data file for the least square, as you can see here. This is the data file for the least square, and then you will take the results, make a comparison from the traverse calculations. This is what we mean by the compass rule or the stepwise, and the least square. So again, we have around 4.5 centimeters, 6.5 centimeters, 7.6 centimeters, the differences. And the differences is because that the least squares, they are a better solution, and these values what we are going to take and give the people for them to use, because the least squares, it does the whole thing in one comprehensive run. Together everything is done, so no errors are inherited from one step to the other. Again, we will see the differences, and the differences we explained this so many times. Now, this is the last